So we now have almost all the tools we need to define a Poisson point process, which is something much more general than what we saw in the real line. But I said almost everything because there's still something missing, which looks like a technicality, but it's worth spending some time on it, which are the point measures. So point measures, is the space in which our Poisson point process is going to exist. So just like the Brownian motion, Bt was an element of C01 when we evaluated it in a sample space. So we're taking random continuous functions when we're talking about the Brownian motion. What is it that we're going to obtain when we talk about the Poisson point process? It's going to be a random point measure. So this requires us to define the space and sigma algebra and talk a little bit about measurability issues, unhappily, but it's going to be brief. So first we start with our underlying space. So this can be thought as like the real line for the examples that we already saw, or S could be R2 for a very interesting example as well, or a manifold. So S is our space where the points will be. So you can think that we're defining a process with several points on top of S. But S is not our probability space. Our probability space is this space of points. So we're going to require S to be locally compact and have a countable base. Okay, so S is a reasonable space. Most of the spaces we have in mind are much more reasonable than just requiring locally compactness and countable base. And this is the space that we're going to be interested in. It's the space of all the measures that can be written as a sum of deltas. And I'm not saying if the sum is infinite or not. I'm just asking that the measure of every k compact should be finite. So this is the space of locally finite point measures. So you don't want, for example, in the real line, when S is the real line, we don't want points to accumulate somewhere and blow up. We want something that is finite for every compact. But okay, we now have a kind of weird space. It's reasonable, right? An element like this, M, can be drawn like that. So every xi you mark a point. But remember that it's counting multiplicity. So if there are two occurrences of x in the same place, the measure is going to fill it. It's going to have twice delta Dirac in that point. So this is interesting to keep in mind. But what about measurability stuff? What is the sigma algebra that we use on gamma? So we're going to define sigma algebra M to be the sigma algebra generated by what we call the evaluation maps. So I'm going to explain what an evaluation map is. So first recall that S is a space, a topological space that we endow with the Borel sigma algebra. So A is the Borel sigma algebra of S. So for every B in A, so we have here S and here B, we're going to define the evaluation map GB, which takes some M and returns M of B. So it's a bit of a inverting thing. And what's the domain and counter domain of G, right? The domain is gamma and it goes to Z plus union infinity. There could be, so what G says is like how many points are inside B. So it's an integer, could be 0, it could be also be infinity. So this is the evaluation map G, and remember that G is going from gamma to some space where we have a sigma algebra, so we can define a sigma algebra on gamma by these evaluation maps. So this sigma algebra, another way to say, is the smallest sigma algebra making all the GBs measurable. So this is what it does, and we are going to introduce some notation here to kind of not use G so much, because G is kind of ugly. So when we have a random element, so this is our like random variable, but not a random variable, it's a random point measure. So if this is measurable, so we have a probability space with some sigma algebra, we have this space gamma of locally finite point measures, so we can talk about M, uppercase M, being measurable. And in case this is measurable, we call it a random point measure. Just like if M from omega to R is measurable, we call M a random variable. Now we call it a random point measure. And we're going to bypass the G a little bit. When we have this M, we're going to denote M of B. This is a bit of an abuse of notation, right? To denote M of omega. This is now an element of gamma applied in B, because now it's a measure and you can apply it on B. So it's how many points fall inside B. Again, just written in a more compact way, and it's related to G of B, because if you go to the, if we draw like where things are going, this is omega, this is going to gamma, space of point measures, and then we have here GB that goes from gamma to Z plus union infinity. And here we have M. So MB is just bypassing everything here. This is M of B. Takes an omega and returns the number of points directly. So another way to say is that MB is GB composed with M. Okay, now this is clear that if M is a random element and GB by definition is measurable, because the sigma algebra introduced on gamma is the one that makes all GB measurables, so this is a random variable because it's a composition of two measurable maps, M and G. Now the opposite is also true. So lemma, if for every B in A, M of B, or maybe I should write, now should be more picky and write GB composed with M, is measurable, is a random variable, then M is measurable. So this is a nice criterion to prove that something is a point measure. Just look if the evaluation maps are measurable. And the proof is very simple. Let's recall what is the sigma algebra we introduced that we have to use to prove that M is measurable, right? So M goes from omega to gamma. And what's the sigma algebra that exists here? It's a sigma algebra M, script M. So script M, again, is a sigma algebra generated by the evaluation maps. So another way to say this is the sigma algebra generated by the events GB is equal to K, where B is any set, measurable set in the Boolean sigma algebra of S, and K belongs to Z plus or K is infinity. So this is equivalent. This is the sigma algebra generated by the GBs. Now, what is M? So if we want to show that M is measurable with respect to some sigma algebra here, we have to show that M minus 1 of anything is measurable. So for every, more precisely, right? For every, let's call it D in M, we should show that M minus 1 of D is measurable. But actually we don't have to prove this. This would be too much. It's enough to show that for every D in the class that generates the sigma algebra, so for every GB equals K, so this is the event. So here B is in A and K is integer or potentially infinity. We have to prove that M minus 1 of GB equals K is measurable. So instead of checking every single event here and take the preimage, you can take just the ones that generate the sigma algebra here and take the preimage. And this is very easy because this is exactly GB composed with M minus 1. So this is equal of K. And we are assuming that GB of GB composed with M is measurable. So this is clearly measurable. So it's proved. Okay, so this is some measurability things we want to see, just to, you know, if we are going to, when we are proving things about the Brownian motion, we wanted to have some understanding of the sigma algebra in C01. But this was very easy because C01 was a topological space, very nice. It was a metric space, so we're going to use the Borel sigma algebra. Here we have, you know, M's that go to some stranger space, but we have a criterion now that shows when M is measurable reasonably easy. So let's move on and try to see another important type of result, which is when two measures are the same. So let's recall for the Brownian motion, if we had two measures that give us random functions, the finite dimensional distributions were enough to determine the measure. So if we could equate the finite dimensional distributions of these two beasts, we would be able to claim that these two distributions are the same. And here we have something very similar, but the finite dimensional distribution between quotation marks is slightly different. So it's a proposition that says if M and M prime are random point measures satisfying that M of B1, recall this is a random variable, up to M of Bn as a vector of a random vector, right, in R in Z n union infinity, has the same distribution as the same thing or with M prime, So if these two things have the same distribution, for every b1 up to bn in A, then m has the same distribution as m prime. So this is an easy way to check for the equality of distributions between m and m prime. Just check these random vectors here. You have your probability space, your ambient space S. You pick some sets b1, b2 up to bn, and just look at the vector number of points falling in 1, 2, 3 up to n under the measure m and under the measure m prime. If for every b collection b1 to bn this has the same distribution, then the measures m and m prime are the same. So how do we prove this? So we have seen Dynkin's theorem that essentially says that it says something about a lambda system, a pi system, the sigma algebra generated by the pi system, and so on and so forth. But it has a corollary that is easier to remember. If m of let me now state it differently. If the distribution of m I'm gonna call Pm. If Pm of k is equal to Pm prime of k for every k in script k, a pi system, then Pm of k is equal to Pm prime of k for every k in the sigma algebra generated by script k. So this is a corollary of Dynkin's, because this equality here is something that characterizes a lambda system. So we can use the Dynkin's theorem to get this statement. So all we have to do is to check the equality of these probabilities in a pi system that is rich enough to generate the whole sigma algebra. So why this is not so good to look at? Because this could be a very strange event. So k could be like there's 3 points in the first ball, and the number of points falling somewhere weighted by the position they fall is equal to pi. I don't know. So it can be a very complicated event. So if we restrict to a pi system that is simple enough, we can start writing this in terms of the MBs that the proposition uses. So that's why we're going to define this family of events. So this is going to be the event that MB1 up to MBN as a vector, right, belongs to A. So here we have to choose what we are varying here. So we are varying A in the Borel sigma algebra of Z plus union infinity. We are choosing B1 up to Bn in the sigma algebra of S. So here we have a nice family. We have to check two things. So first, does the sigma algebra generated by D is equal to the full sigma algebra? And second, is D a pi system? So this is what we have to check, and it's actually going to be rather easy. So first, why the first is correct? So remember that M is the sigma algebra generated by events of the type GB equal K for B in A, sorry, script A and k in z plus union infinity. So that was one way to write the sigma algebra M. So you see that GB equals K is exactly MB, M of B equals K. So this is an event of D where we are using n equals 1. So everyone that we are using to generate M is in D. So indeed D generates M. Now 2, why is D a pi system? So if we are intersecting two elements of D, we can write them as M of B1, M of Bn belongs to A. This is one event on D, and the other event is M of B prime 1, the vector, right? M of Bn prime belongs to A prime. So here you have to so let's not call it n prime, let's call it M. So we have different lengths. One goes from 1 to n, the other goes from 1 to m. Now different sets, b1 to bn, the other is b1 prime to bn prime, and different elements of the Euclidean space, A and A prime. If we're intersecting them, we can write this as it's a bit ugly but not much. We join these two vectors, m of b1 up to m of bn. Then we continue the vector with the b primes up to b prime m, and we ask this big vector to be in A times A prime. And you see this is also an element of D. So this is indeed a pi system, because we managed to write the intersection as an element of itself, and it generates a sigma algebra, so it's enough to check equality only on D according to Dynkin. So we now have essentially the basic tools we need to talk about random elements of the space gamma, or in other words, random point measures. So random point measures have an easy way to check that they are measurable, that they are actually random point measures, and also an easy way to check for equality. So we are ready to continue in the next class with the construction of the Poisson point process, which is going to be nothing more than a random point measure that has a very specific and magical distribution. So see you in the next class.